So last time we just were talking about this, and what we said was that yeah, it's not that these two fall side by side because they have the same force of gravity on them. They don't, in fact. I've got to get my pen back. Sorry. They don't, in fact, have the same force of gravity on them. What they have is double the force and double the inertia. So they, so yeah, the force is that force is bigger than that force, but that inertia is bigger than that inertia. So it's the ratio. And we say the fact is that if the mass is doubled, the force of gravity is doubled, and the inertia is doubled. If the mass is tripled, the force of gravity is tripled, and the inertia is tripled. So the acceleration is due to that ratio. It's how does your force compare with your inertia, basically. So it's kind of an interesting way of looking at it. So in a vacuum, so here's a vacuum tube, a coin which is metallic and not very heavy, but metallic, and a feather fall side by side. Would it be correct to say that equal forces of gravity act on both the coin and the feather when they are in vacuum? So what do you think? Is it that they've got the same force on them, so they fall side by side? Or what's going on? Coin, feather. I could say a can of beans and a feather. It's the same thing. Coins can have different weights, but cans of beans tend to be, I suppose I should say, a chicken feather, so we can pick that out. But what do you think? I got 9 votes. I know some people checked in, so we'll go for another. I'll go up to 45. So what do you think? So it says, would it be correct to say that equal forces of gravity act on both the coin and the feather when they are in the vacuum? So what's going on here? And we're going to say what we're going to say. Ooh, that's evenly split. So let's talk about this a bit. So, and this is, I think it's just traditionally they always say coin and feather, but frankly, coins can be really light. And I think when this came from was back in England when they had pennies which were about the size of a pizza. You know, they were like big coins and tiny feathers. So if I said a can of beans, I think it'd be pretty clear that this is a big force and that's a small force. So just because they're in vacuum does not do anything to the amount of weight that an object has. It's still got the same weight it has in the air. So would it be correct to say that equal force of gravity acts on both the coin and the feather? Absolutely not. No, they are different. They are different weights. The fact is it might be 10 times the weight. The can of beans might have 10 times the weight of the feather, but it's got 10 times the inertia. And so, and no air resistance, because the vacuum is getting rid of the air resistance, so it's making it really work well. So that's where we've been up to now with air resistance. Let's ignore air resistance. So now let's talk about air resistance. So what we say is acceleration in less than g. So it's non-free fall. So you're not going to fall downwards with an acceleration of 10 meters per second squared downwards. It might be you're going to fall downwards with an acceleration of 5 meters per second squared. You're still going to weigh as much, but you're going to have more drag because now we're adding air resistance back in. Objects that fall through a liquid, and we can think of the atmosphere as a very thin liquid, but it could also be oil or it could be water, experience a drag force. The drag force depends upon the frontal area. So if I have a weird shape, I imagine taking that cross-sectional area. I'm going to draw it a bit like I can see it. It's that it's actually that cross-sectional area. It's cross-section at the widest point. And it depends on the speed of the falling object. That seems a little bit strange, but it turns out the faster you go, the less time these particles have to get out of the way. And so you kind of hit them harder, and it's like running through a crowd. If I try to run through a crowded room, I'll have a much harder time than if I try and run through a less crowded room. Yeah? So, why? Well, more particles, etc. So what's my velocity going to... Well, this is not... I'm not explaining this well at all. Bad example. Yes. If I'm being rained on by small coins, I will have less effect. No, that's not good either. It just works out that it's to do with velocity. The faster you go, the more drag that an object has. I can't think of a good... I'll think of one for next time. So we say, initially, an object has no velocity, so no drag force. So its acceleration is 10 meters per second squared downwards. As the speed, at speed, its drag force increases, and so its acceleration decreases. There's less net force. Remember, F net is the sum of these two. And this guy is cancelling out some of that guy. So there's less net force, so less acceleration. And at terminal speed, not when you're stationary, but when you're moving at a constant, the fastest speed you're going to have, but it's a constant speed, then the drag force equals. So this guy completely cancels out that guy, and we have no acceleration. So we say, for two identically shaped objects, the terminal velocity is greater for the greater weight. So what's going on there? If I have that object, and I have that object, and this one is light and this one is heavy, then this one has a bigger weight. And so you reach your terminal velocity when you balance. So I reach my terminal velocity when my F drag is that big in that case, and I reach my terminal velocity when F drag is that big in that case. I got to go faster. If the cross-sectional area is the same, I got to be going faster to get this bigger drag force. So, two identically shaped objects, the heavy one has the bigger terminal velocity. Okay, so that's kind of interesting. A skydiver has a terminal speed of about 55 meters per second, which I think is about over 100 miles an hour. It's just the way it is. You know, if they point their head downwards, their terminal velocity is much higher than if they do that star-shaped thing where they hold their arms out like that. So, controlling their terminal velocity. Oh, yeah, okay. So last bit. So a skydiver jumps from a high-flying helicopter. As she falls faster and faster through the air, does her acceleration increase, decrease, or remain the same? So imagine jumping out of the helicopter and ask yourself, let's draw a picture of it. Jumping out of the helicopter, we have our weight, and we have a little bit of a drag force. And then a bit later, we have our weight, and we have a bigger drag force. And a bit later, we have our weight. These should all be the same size. And we have our bigger drag force. And ask yourself, what's going on with the acceleration? Is it a big acceleration, a small acceleration? What's going on with the acceleration? And then I want you to vote. I know we're almost out of time. I got like a minute, so this is going to be a 30-second vote. I want to get to the next question because I think the next question is hard. So I'll do it for another 5 seconds and then we'll stop. 3, stop. Okay? So what do people say? Ooh, mainly B, little bit of A, bit more of C. So when I look at this, I say let's get a slightly different coloured pen so you can see my thinking. Let's go to purple. So when I look at this, I'm going to go, oh, that's going to be minus 10 meters per second squared, because this is not worth considering, yeah? This is going to be less of a net force, so that's going to be minus 5 acceleration meters per second squared. And this is balanced, so 0 meters per second squared. So what's happened to my acceleration? It's gone from minus 10 to minus 5 to 0. So, sorry. So as she falls faster and faster through the air, does her acceleration increase, decrease, or remain the same? Bad question, I think, because the number is decreasing, yes? 10, 5, 0, so that would be decreasing. But if you look at the number, it's minus 10, minus 5, 0. So you could actually justify increasing on a number line. Okay? So I should have said, does the magnitude of the acceleration increase, decrease, or stay the same? What's the numerical value? And that's definitely decreasing. Agreed? Yeah, cool. And then the last one, I'll do this with you. I'm not going to do it on a clicker. Basketball is made of styrofoam. Basketball is made of lead. They're dropped from the top of a building. Which has the greater terminal velocity? So this is light and this is heavy. Which has the greater terminal velocity? This is little weight. This has huge weight. So which has the greater terminal velocity? What the heck, we'll do the voting. Which has the greater terminal velocity? What do you think? I'll give you let's get to 10 people. Let's see how it goes. We'll have a representative 10. Oh, we've got to back up now. No, it's okay. Just go on. Let's have a look. Oh, mainly B. Yeah, it's the lead. What happens is that in order to balance off this big weight, you need a big terminal velocity. Yeah, because you need a big drag force.
But I thought the styrofoam, because we did this in lab, the styrofoam would reach terminal velocity first because it weighs less.
Oh, it reaches it sooner, and it's a lower terminal velocity. So it reaches it sooner. Yeah, cool. Cool. Please, and the clicker's back in. Thanks ever so much. Oh, you need your test. I'm sorry, I forgot all about that. I'm sorry, I've gone way over. So as I call your name out, please wave your hand. So, Macario. Yeah. And Papa. And Abalum. Oh, Saxon. And Eduardo.
Right here.
And Roger. And Anne. And next we're going to have I think it's Eugen Wynn. Yeah, did I say that right? Yeah, sorry, L-U-E-N. Oh, how do I say that? Oh, yeah, no, yeah. Well, the first name. Oh, that's fine. Okay. And sorry then, Amanda. Sorry, I'm not mispronouncing anything today. Lydia. Yogita. And then Yuyan, Lee. And Ali. And then Michael. Kevin. Craig. Cole. Jonathan.
Can I take my test too?
Please, yeah, take your test, yeah. You can look at the test because it's like there's no score on there. Ruben. Anthony. And then Connor. Did I say that? Yes, right. And then Dominic. Shannon. And then no Eugen Wynn. Okay. So did you find it?
I just was curious which one.
So let's look. What's your name?
Wilt. Oh,
There you go. That's luck, isn't it?
Yeah, it is.
So,
Thank you.
and I'll put the key up so you can compare the key exactly. Oh, sorry.